The first thing to understand when working with series is the difference between a sequence and a series. A sequence is a set of numbers. For example, the sequence a(n) equals 1 over n is equal to a set of numbers 1, 1/2, 1/3, 1/4, and so on. A series is a summation of numbers. For example, the series of 1 over n from n equals 1 to infinity is equal to 1 plus 1/2 plus 1/3 plus 1/4, and so on. To see if a sequence converges, you take its limit as n approaches infinity. To see if a series converges, you need to use one of these tests. The first thing we do when working with a new series is test for divergence. We do this by taking a limit of the sequence as n approaches infinity, and if that limit is not equal to 0, then the series will diverge. This test only checks for divergence and doesn't tell us anything about what will happen if the limit of a sequence is equal to 0. Here are some examples. For our first example, the limit of inverse tangent of n as n approaches infinity is equal to pi over 2, which is not equal to 0, so this series diverges. For our second example, the limit of negative 1 to the n as n approaches infinity is undefined, so this series diverges. For our third example, the limit of 1 over n as n approaches infinity is equal to 0, which means we don't have enough information to see if this series converges or diverges yet. A p-series is a series of the form 1 over n to the p, which converges if p is greater than 1 and diverges if p is less than or equal to 1. This includes the harmonic series, 1 over n. Here are some examples. For the series 1 over n squared, our p-value is 2, which is greater than 1, so this series converges. For the series n to the negative cosine of 6, we rewrite it as 1 over n to the cosine of 6 and see that our p-value is cosine of 6. Rewriting stuff using the rules about exponents, summations, and fractions is something you're going to be doing a lot. We know cosine of 6 is less than or equal to 1 because cosine of 6 is approximately 2 pi. You can also double check this by plugging this into a calculator. Because p is less than or equal to 1, we know that this series diverges by the p-series test. A geometric series is a series with a constant ratio, which converges to a over 1 minus r if the absolute value of r is less than 1, and diverges if the absolute value of r is greater than or equal to 1. Here's an example. For the series 1 plus 7 to the n over 8 to the n, we start by rearranging the terms so that it matches the pattern we're looking for. It is important that if we're going to be using this equation, we make sure that all the terms in our series match. For example, it is not enough to leave n as an exponent if a geometric series requires an n minus 1. That's why we factor out a 1/8 and a 7/8 so that all the terms in our series match. Because 1 over 8 and 7 over 8 are both less than 1, we know that this series will converge. The comparison test states that you have two series, AN and BN, with one of them larger than the other. Then if the larger one converges, the smaller one also converges, and if the smaller one diverges, the larger one also diverges. For the first example, we compare a series to 1 over n by using the inequality 8 over 6n minus 1 is greater than 8 over 6n. This gives us an an that diverges by the p-series test, which means that our series 8 over 6n minus 1 diverges by the comparison test. For our second example, we compare a series to 1 over n squared, which is a series that converges by the p-series test. So we know that 1 over n squared plus 1 converges by the comparison test. For the series negative 1 to the n over n, the limit of 1 over n as n approaches infinity is equal to 0, and 1 over n plus 1 is less than 1 over n for all n. Therefore, this series converges. We can estimate the error of the first k terms of an alternating series by looking at the next term. For example, if we want to know how many terms of this series we need to add up in order for our error to be less than 0.05, we let our k plus 1 be equal to 20, so ak plus 1 is equal to 0.05, and we see that we let k plus 1 equal 20, so ak plus 1 equals 0.05, which means that 19 is the smallest amount of terms needed for the error to be less than 0.05. An alternating series has a sequence with alternating signs and converges if the absolute value of the terms of the sequence are decreasing and approach 0 as n approaches infinity. For the root test, we find our L, which is equal to the limit as n approaches infinity of the nth root of our sequence. If L is less than 1, the series converges. If L is greater than 1, it diverges. And if L equals 1, it's inconclusive. Here's an example. For the series negative 1 to the n minus 1 over inverse tangent of n to the n, we see that our L value is equal to 2 over pi, which is less than 1. So this series converges. For the ratio test, you find your L, which is equal to the limit as n approaches infinity of the absolute value of an plus 1 over an. If L is less than 1, the series converges. If L is greater than 1, it diverges. And if L equals 1, it's inconclusive. Here's an example. For the series x to the n over n, we see that our L value is equal to the absolute value of x, which is less than 1 in an interval between negative 1 and 1. Because the test is inconclusive at negative 1 and 1, we need to check each of these values individually. For x equals negative 1, this series converges by the alternating series test, and for x equals 1, this series diverges by the p-series test. So this series converges for the values negative 1 is less than or equal to x is less than 1.